All right, here we go. Our last video of Unit 1. That's the good news. The bad news is, deal with it. It's going to be a long one, so too bad. So, let's talk a little bit about what's called spectroscopy. So there's a device called a spectrophotometer. If you want to look that up, spectrophotometer. A spectrophotometer, basically. And what this device does is you put what's called a cuvette, and I would show you this in school if we were there. So you put a cuvette that's filled with a liquid, okay? And this liquid is colored, okay? So it's going to have some color to it. Might be blue, doesn't matter the color. And what it does is it shoots a ray of light through that colored species, and it has something on the other end that measures how much of that light gets through there. Okay, and so over here it measures how much light gets through. Okay, and what that does is it can tell you basically how concentrated that solution is. If it's really concentrated, then not a lot of light's going to get through there. Okay, if it's not concentrated, then it will, a lot of light will make it through there. So there are some different things that you can tell from that. One of them, and these are kind of just basic things. We're going to get to this in a little bit more detail here in a minute about how the spectrophotometer works. Okay, so depending on the type of radiation that you use, so the type of light that's coming through here, you can tell some different things. Okay. With photoelectron spectroscopy, which is another type of spectrophotometer. I know I erased most of that. Spectrophotometer. Okay, PES is a type of spectroscopy that uses a spectrometer. Okay, and what PES does is it tells you about what are called electronic transitions within the atom. Okay, and obviously those electronic transitions tell you about the electron configuration. Okay, and so PES is a type of what's called visible spectroscopy or even ultraviolet spectroscopy, and it tells you about electronic transitions, which is, again, the first shell, second shell, third shell, etc. Okay, so ultraviolet, the letter U, I'm going to use something to try to help you remember this, and visible, so you can think of this as ultraviolet or visible, produces electronic transitions. Okay, remember that, UVET. Again, an easy way that I remember this one is if somebody says, if you want to ask someone if they're a veterinarian, you might say, "You vet?" I know it's stupid, but it'll help you remember it. Okay, and that helps you remember that ultraviolet and visible light produce electronic transitions. Okay, another type of energy or electromagnetic radiation is called infrared spectroscopy. What that produces is it produces electronic vibrations. It causes the electrons to vibrate. Okay, and so infrared causes vibration. So IRV. So UVET is one of them, ultraviolet electronic transitions. What do you do in the summer? IRV, which means I go in an RV and I travel around the country, which I don't actually do, but you could. Okay, so infrared IR produces vibrations. Okay, so that's our second one. And then our third one is that microwaves, which again, another type of electromagnetic radiation. If you need to look at that, go back towards the beginning here of Unit 1 and you can see the electromagnetic spectrum. So microwaves even lower in energy, so they have the longer wavelengths. And what microwaves can do is they can produce what are called molecular rotations. And so think about a microwave, and inside a microwave you put your food in there, and it probably has a little dish in there, and that thing turns in a circle. And so when I think of this one, I think of microwaves rotate. Okay, and that's all you need to remember. Okay, so here's our three dumb ways to remember it. Microwaves rotate, IRV, and you're a veterinarian. Okay, so that's just one of those You might see one question about that on the AP test. Hopefully you don't, but if you do, if you remember those three things, you're probably fine. Ultraviolet, electronic transitions, infrared vibrations, and microwaves produce molecular rotation. Okay, now this is a very, very important law that we've got here that deals with, again, a spectrophotometer. Okay, this is an equation that is given on the equation sheet. If you look on your equation sheet, it is on there. Okay, and the equation stands for capital A, which is the absorbance. So remember that drawing I had earlier. How much of that light gets absorbed down here? So the light, there's a light source over here, so you've got a light bulb over here, and that light bulb is producing light that's traveling through this colored species, and then it's being, again, detected on the other side. And how much of that gets through is how much of that light gets absorbed. Okay, so that's our capital A. So how much light gets absorbed is equal to three things that are multiplied together. First of all, there's that weird looking symbol here, and that is just a constant, similar to the gas constant. Okay, it does depend on the nature of the material under test, which means it can vary depending on what the substance is that's in that in the test tube, or the cuvette is what it's called. Okay, B is what's called the path length. Okay, what's the distance across that? So again, a test tube, typically we call it a cuvette, actually. Cuvette, okay, is the distance from here to here. Okay, that is the path length of that letter B there. Okay, and then the last one, the real important one, is that C, and that stands for the concentration that is measured in the molarity of that substance. Okay. So really, the two things that you're really looking at here are absorbance and concentration. And if you think about it, the greater the concentration, the more absorbance there's going to be. There's less of that light that's going to travel through there, and so more of that light will get absorbed, and that's pretty typical to what you'll see. Okay, so when absorbance measurements are made at a fixed wavelength, so remember, this kind of goes back to what we were talking about earlier, that it deals with wavelength and frequency and energy, okay? So when absorbance measurements are made at a fixed wavelength in a cell of constant path length, which they are, that means that and they used to use the smaller, this equation right here, that weird looking symbol used to be a lowercase a, and clearly I messed up. So it's not that lowercase a, it is that weird looking kind of an E looking thing. So both the path length and that constant are obviously constant. And so therefore the absorbance A is directly proportional to, again, C, which is the concentration. So if a solution of a compound obeys this law called the Beer-Lambert law, a plot of the absorbance on the y-axis, you can see it here, there's our absorbance right here, versus the concentration does give a straight line with a slope of, again, not lowercase a, that E times B. Okay, the y-intercept is 0. Obviously, if the absorbance is 0, the concentration is also 0. And then you can use this graph to determine, based on the absorbance, you can determine the concentration. Pretty easy, okay? So there's the graph right there that we can look at, and we're going to look at a couple of example questions here in just a second. Okay, one of the settings on a spectrophotometer is the wavelength. Okay, the wavelength of the light needs to be set where you can read the maximum absorbance, okay, where the absorbance is going to be the highest. Okay, so here's a graph here that shows this. So it's showing that the absorbance is greatest at a wavelength of right around, let's say 510 or so. Okay, and what that means is on the spectrophotometer, you actually turn a knob and you set the absorbance, or you set the wavelength at 510 nanometers. And then at that wavelength, more of that molecule, more of the light will get absorbed at that wavelength. Okay, now sometimes there's multiple substances in a mixture. Okay, so let's say that you have two different things that have different colors. You want to make sure that the wavelength is set at the whatever one they're asking you about. If they're asking you about Fe2 plus and you have a mixture of Fe2 plus and Ag plus, you want to make sure that the spectrophotometer is set at the right wavelength to maximize the absorbance of Fe2 plus and try to minimize silver as much as possible. Okay, so let's say we have an example here. We say a student plans to conduct a spectrophotometric analysis to determine the concentration of Cu2 plus. Okay, so we want to know about the Cu2 plus. But the solution also has some cobalt in it as well. And cobalt, CO, is soluble. And so we're going to have some CO ions floating around in there as well. Okay, and the student is given this curve right here. So you're looking at this curve right here. So we can see that if we wanted to know about cobalt, well then absolutely we would set the wavelength right where the absorbance of cobalt is the highest, right at around 500. Okay, if we want to know the absorbance of copper, which is what they're asking us about here, then we would love it if we could have a measurement right at about 815, 820, somewhere around there. Okay, and this is where they try to trick you. It says the spectrophotometer available to the student has a wavelength range. That means it only goes a range between 400 and 700 nanometers. What wavelength should the student use to minimize the interference from the presence of the cobalt ions? Well, you want to say 810, 820, somewhere around there. But remember, the range is only from 400 to 700. Really, really easy to mix that up. Okay? So, what's the correct answer? Well, between 400 and 700, what's going to give you the maximum absorbance of copper and the least absorbance of cobalt? Absolutely 700. Okay? If you said 800 and something, you did not get, this is from a real AP test, you did not get credit. For any number above 700, they didn't give you credit for it. Okay? Now, they don't ask you to explain it, so I'm not going to. Okay? But if I had to explain it, I would say, because again, the range only goes up to 700, and the maximum copper absorbance occurs at 700 while minimizing the cobalt as well. Okay, so here's another example using an absorbance versus concentration here. And again, sometimes I'm not sure if we've talked about this or not, because clearly I understand it, but those square brackets mean the concentration. So it says a calibration plot of the absorbance at wavelength 590 nanometers, and probably that number doesn't matter. They're just telling you that we set the wavelength at 590. Okay, versus the concentration. So we've got absorbance versus concentration of something called BPB. We don't know what that is. We don't care what that is. Okay? Based on the best fit line shown in the graph, what is the approximate absorbance of a solution in which the concentration of BPB is 3.5 times 10 to the minus fifth? So here's 3 times 10 to the minus fifth. Here's 4. So I'm going to say that right there is 3.5. So literally I'm just going to go up to here. I'm going to go over to here. Clearly, what is the approximate absorbance? 0.7. Okay, there's no math to do, no nothing. Okay, a student measures the absorbance of a solution of BPB of unknown concentration in order to determine the concentration of BPB in the solution using the calibration plot above. If a fingerprint remains on the cuvette, so think about that. If you touch that test tube or that cuvette and the light is trying to get through there and it's measuring how much light gets through there, and you've touched that and you didn't wipe off your fingerprints, does that mean more light is going to get through or less light is going to get through? Hopefully you realize less light is going to get through. So if a fingerprint remains on the cuvette and in the path of the light in the spectrophotometer during the measurement, what would be the effect on the estimated molarity of BPB? Justify or explain your reasoning. So, is the absorbance going to be higher, lower, or the same as what it's supposed to be? Okay, so remember the absorbance is how much light doesn't get passed through. It's how much light gets absorbed. Okay, so to me that means that, wow, some of that light is gonna hit my fingerprint and not make it through. That's gonna make the absorbance higher than what it actually is. And if the absorbance is higher than what it's supposed to be, then think about that equation, A equals BC here. If this is higher than what it's supposed to be, then what's that going to do to the concentration? Again, those are constant. Well, it's going to appear to make that, if it's supposed to be 0.4, but the absorbance is actually 0.6, what does that do to your concentration? Of course, it makes it higher. Okay, so what would be the effect on the estimated molarity of BPB? It would be too high or higher than it should be, and then explain your reasoning, because more light would get absorbed, and more light getting absorbed, hopefully you're writing this down, more light would get absorbed, and if more light gets absorbed, if the absorbance is greater, then the concentration is also going to appear to be greater.